Hi there! In this video I'm going to talk about the Jacobi method for solving system linear equation. So if you've watched the Gauss-Seidel method for solving system linear equation that I published a while ago, you will probably know how to do it with the Gauss-Seidel method. And you're going to be advantaged because the Jacobi method is pretty much the same, but it's not going to make use of each and every variable calculated at each and every step of the iteration. Rather, it's going to wait for the next iteration to be completed with all the steps in order to make use of them. So basically the Gauss-Seidel method is going to converge faster than the Jacobi method. Right, so let's crack on. If you haven't watched the Gauss-Seidel method, I strongly suggest you to do watch it. But even if you haven't, it's actually fine. You can understand the Jacobi method even if you haven't watched it. So let's do this. All right, let's start with the matrix, like and random matrix, as we always do, like 4, 1, 0, 0, 1, 5, 1, 0, 0, 1, 6, 1, 1, 0, 1, 4. This is going to be our matrix A. Always call the matrix A. This is a 4 by 4 matrix, so 1, 2, 3, 4, 1, 2, 3, 4. And therefore, we're working in the fourth dimensional space. So our vector x is going to be with 4 components: x, y, z, and w. And it's going to be equal to c, which is, I don't know, 1, 7, 16, 14. All right, so this is basically our system linear equation. So this is actually going to give us 4x plus y equal to 1, x plus 5y plus z equal to 7, y plus 6z plus w equal to 16, x plus z plus 4w equal to 14. So far, so good. I mean, there is nothing new here, just, plain linear algebra. All right, now I'm gonna do exactly like the Gauss-Seidel method. So I'm basically gonna, I'm not gonna find any variable. I'm gonna, try to put x, y, z, and w and find an in function of other variables. So I'm not going to solve the system, I'm just going to find them in function of other variables, just like in the Gauss-Seidel method. So I basically get 4x equal to 1 minus y, 5y equal to 7 minus x minus z, 6z equal to 16 minus y minus w, and 4w equal to 14 minus x minus z. And then I'm gonna get, x equal to 1 over 4 minus 1 over 4y, y equal to 7 over 5 minus 1 over 5x minus 1 over 5z, z equal to 16 over 6, which we are lucky we can simplify as 8 over 3, minus 1 over 6y minus 1 over 6w. Now we have w equal to 14 over 4, which can simplify as 7 over 2, minus 1 over 4x minus 1 over 4z, and this is gonna give me x equal to 1 over 4 minus 1 over 4y, y equal to 7 over 5, minus 1 over 5x, minus 1 over 5z, z equal to 8 over 3, minus 1 over 6y, minus 1 over 6w, and w equal to 7 over 2, minus 1 over 4x, minus 1 over 4z. As you can basically see, I've done like the Gauss-Seidel method. So I basically explicited and I basically found x, y, z, and w in function of the other variables. And I need this in order to start with the iterations. So now I'm going to start with the iterations. And just like in the Gauss-Seidel method, some textbooks actually differ in the way they call iteration and step. Some of them only call, iterations, and they don't take account of steps. Some other count, iteration only when they have done a full cycle of steps, and so on. I'm gonna go for the latter. So let's start. With the iterations. So iteration 1, step 1. Whoops, there we go. So I'm gonna draw a little. There we go. A little table here. You should be familiar with it if you watch the Gauss-Seidel method video I did. So those are going to be our values. Those are going to be our iterations. There we go. I actually computed this on my computer. Textbooks generally give you a starting vector, just like in the Gauss-Seidel method. And in this case, our starting vector are going to be 0.2500, y equal to 1.4300, z equal to 2.667, and w equal to 3.500. Okay, so those are going to be our starting point, just because I computed it and I know that are going to be good starting point. Anyway, you can start like the Gauss-Seidel method. You can start with everything set to, I don't know, 0, or everything set to 1. It's up to you. It's fine. It's just a matter of how long it's gonna take to converge to your desired result. So unlike the Gauss-Seidel method, I'm gonna basically underline everything just like this Gauss-Seidel method, but unlike it, I'm gonna use two colors this time. You're gonna see why in just a moment. So I basically underlined everything because I have to find each and every variable. But I'm just gonna underline the following one, because this is gonna be the one that we're gonna find in this iteration. However, we're not gonna use it. We're not gonna use in this step of the first iteration. We're only gonna use in the second iteration. So we have to complete all the steps first, and we're not gonna update our variable. So let's start. Okay, x equal to, I'm gonna use this equation here. So I'm gonna see what x is and what it's dependent by. So x equal to 1 over 4, which is a scalar. It's not dependent by anything. Minus 1 over 4 y, so it's dependent by y. And y, our starting point is 1.4000. So times 1.4000. There we go. So x is equal to 0.25 minus 0.25. I'm approximating, basically turning everything, the fraction, into non-functional values, not functional values. So times 1.41 times 1.4000. And therefore x is equal to 0.25 minus 0.35, and therefore x is equal to negative 0.1. And I'm gonna do this using green as a color because this is the value that we had just found, right, for x, but we are not gonna use it in the next step. So iteration 1, step 2. So we're gonna write and make our table. So those are gonna be our values, and those are gonna be our iterations. So we're still gonna have the very same values. So x is still gonna be 0.2500. So unlike the Gauss-Seidel method, in which I would have wrote this new value we have found, in the Jacobi method, we are still gonna use x with the former value. So in this case, it's the value we started with. So y is still gonna be 1.4000. Z is gonna be 2.667, and w is gonna be 3.500. 500. There we go. All right. So in this case, I'm gonna underline this one, and this one. And I'm going to underline the x because we already found a value for x. And I'm going to underline it with green. And I'm going to underline y because we are now going to find the value for y. Right, so y is actually equal to, well, let's see, y equal to 7/5, which is a scalar, it's not dependent by anything, minus 1/5x. So 1/5 times x, so the former x, not the new x, the former x. So 0.2500 minus 1/5z, so it's dependent by z. 1/5 times z, so times 2.667. There we go. And now we are going to solve for y. So 7/5 is actually 1.4. Minus 0.2 times 0.2500 minus 0.2 times 2.667. And now we have y equal to 1.4 minus 0.05 minus 0.5334. And then we have y, which is equal to 0.8166. There we go. And there we go. Iterations. Iteration 1, step 3. So we're gonna go on. And we are still not gonna use the values we found. Those are going to be our values, and those are going to be our iterations. Okay, so we're still going to have x equal to 0.2500, y equal to 1.4300, z equal to 2.667, and w equal to 3.500. There we go. There we go. And I'm now gonna underline only w, which we still have to find, and z that we still have to find. But I'm gonna underline with green x, which we already found, y, which we already found, and z, which we're gonna find now in this very step of the iteration. So z, let's see, z is dependent by this equation. So we have 8 over 3 is a scalar, is not dependent by anything, minus 1 over 6y is dependent by y, minus 1 over 6w, so it's dependent by w. Therefore, we have 8 over 3, so it's a scalar, it's not dependent by anything, minus 1 over 6 times 1.400 minus 1 over 6 times 3.500. So z is actually equal to 2.6666. 6666, yeah, minus 1.6666 times 1.4300 minus 1.6666 times 3.500. There we go. So z is actually 2.6666 minus 2.3332 minus 5.8331. Therefore, z is actually equal to negative 5.4997. There we go. Okay, so let's go on, and now we're gonna go for the iteration 1 step 4. Okay, so there we go. What? There, no, there we go. So iteration 1 step 4, which is the very last step. Values, iterations. Okay, so gonna have x, y, z, and w. I forgot what they are. Okay, so those values here. Okay, so yeah, isn't it tedious when you have to, go to the other end of the page? Okay, to the other side. Welcome to the other side. Okay, so x is 0.2500, y is 1.400, z is 2.667, and w is 3.500. There we go. So now I'm just gonna underline with blue the very last one because I'm gonna have to find it, and I'm gonna underline with green what we have just found, and w which we are gonna find now. We're gonna find now. So w is equal to, well, let's see. This is the equation for w. So 7 over 2 is a scalar. It's not dependent by anything. Minus 1 over 4 x, so it's dependent by x, minus 1 over 4 z, so it's dependent by z. Therefore, w is going to be 7 over 2 minus 1 over 4 times 0.2500 minus 1 over 4 times 2.667. There we go. Now we have w equal to 3.5 minus 0.25 times 0.2500 minus 0.25 times 2.667. And then we have w equal to 3.5 minus 0.0625 minus 0.6667, and therefore w is equal to it's equal to 2.7708. There we go. Okay, So now we have found all the values for x, y, z, and w. Then we can go. We have finished all the steps, and we can go to the iteration 2. So iteration 2. Oh, well, this one. Iteration 1. Iteration 2. Step 1. Okay, so basically, since we have found all the values for the iteration 1, and we can proceed with the iteration 2, we're basically gonna change the values and use at least the very last, the one that we have just found. So those ones are all gonna be updated, and we're gonna use the new one. So let's write our table now. These are going to be our values. They're going to be our iterations. So x, y, z, and w. Okay, so you see, so this one and this one. So x now is going to be negative 0.1. Y is going to be 0.846. Was it 8.4? Yeah. Oh, no. 8.166. 8.166. I'm sorry. 8.166. Yeah, isn't it tedious when you have to, go to the other side of the sheet of paper? Okay. Z is equal to negative 5.4997. So negative 5.4997, and W is over here. So it's 2.7708. Now I'm gonna underline in blue all of them, because we still have to find all of them again. I'm gonna underline in green only the very first one, because it's the one that we're gonna find in this very step of the second iteration. So x is equal to, well, let's see. 1/4 is scalar, it's not dependent by anything, minus 1/4 y, so it's dependent by y. So 1/4 is a scalar, it's not dependent by anything, minus 1/4 times y, so times 0.8166. Therefore, x is equal to 0.25 minus 0.25 times 0.8166. So x is equal to 0.25 minus 0.2041. So x is equal to 0.0459. So there we go. It's our new value for x, but we're not gonna use it. We're not gonna use it for the whole second iteration. So iteration 2, step 2. So we're still gonna write and draw our table. Oops, there we go. So values, iterations. So x is still gonna be negative 0.1, y is still gonna be 0.8166, z is still gonna be negative 5.4997, and w is still gonna be 2.7708. But now I'm gonna underline only w, z, and y, because those are the ones that we still have to find. I'm gonna underline in green x, which we have already found, and y, which is the one that we're gonna find in this very iteration. So y is equal to, well, let's see. Y equal to 7/5 is a scalar, it's not dependent by anything, minus 1/5 x, so it's dependent by x, minus 1 over 5 z, so it's depended by z. So therefore, y is actually equal to 7 over 5, is a scalar, it's not dependent by anything, minus 1 over 5 times negative 0.1, which is the x, minus 1 over 5 times z, which is this one, so negative 5.4997. There we go. So y that is equal to 1.4 minus 0.2 times negative 0.1 minus 0.2 times negative 5.4997. So y is equal to 1.4 plus 0.02 plus 1.0999. So y is equal to 2.5199. So this is gonna be the new y, but we're not gonna use it for the whole iteration 2, as I said before. So iteration 2, step 3, the last but one. Okay, so values. By the way, I'm gonna stop after the full iteration 2, because there's no point in going any further. I mean, if you are a calculator, like if you're a computer, you can run this like several times, like many iterations, so it makes sense. But for a human being, for a deeply floated human being like me, no, like no. Okay, so x is still gonna be negative 0.1, y is still gonna be 0.8166, y. Z is still gonna be negative 5.4997. So the NW is still gonna be 2.7708. And now I'm gonna underline step 3, so only those two, so the Z and the W, which we still have to find, and I'm gonna underline with green x, y that we just already found, and z, which is the one we're gonna find in this very moment. So z equal to, well, let's see. This is the equation for z. So 8 over 3 is a scalar, is not dependent by anything. Minus 1 over 6 y is dependent by y, minus 1 over 6 w, so it's dependent by w. And therefore, my equation for z is 8 over 3 minus 1 over 6 times 0.8166 y minus 1 over 6 times 2.7708, so w. Therefore, z is actually going to be equal to 2.6666 minus 0.1666 times 0.8166 minus 0.1666 times 2.7708. Okay, so z is going to be equal to, well, 2.6666 minus 0.1360 minus 0.4916, and therefore z is equal to 2.069. So this is going to be our new value for z. And now we're going to compute the very last iteration. All right, so it's going to be the very last iteration. So iteration, well, the very last step of the second iteration. So iteration 2, step 4. It's going to be our table. Oh, there we go. Values, iterations. So x is going to be equal to negative 0.1, y is equal to 0.8166, z is equal to negative 5.4997, and w is equal to 2.7708. So I'm just gonna underline w this time. I'm gonna underline with green all the values that we have already found, plus w, which is the value that we're gonna find in this very step, the last step of the second iteration. Right, so w is actually gonna be, well, let's see. This is equation for w, so 7 over 2 is a scalar, it's not dependent by anything, minus 1 over 4x, so it's dependent by x, minus 1 over 4z, so it's dependent by z. So w is equal to 7 over 2, as we said, which is a scalar, is not dependent by anything, minus 1 over 4 times negative 0.1 minus 1 over 4 times negative 5.4997. Therefore, w is going to be equal to 3.5 minus 0.25 times negative 0.1 minus 0.25 times negative 5.4997. So w is going to be equal to 3.5 plus 0.025 plus 1.3749. So w is actually going to be equal to 4.8999. And we have just found our new and last value for w. So right now we finished up the second iteration, and so we're going to have x equal to this one, so negative 0.1, y equal to 0.8166, 0.8166, z equal to this, so negative 5.4997, and w actually equal to this, 4.8999. There we go. So as you can basically see, the Gauss-Seidel method has a clear advantage over the Jacobi method that we have just computed, because, you know, in the Jacobi method that we have just done, oh, there we go. Oh, no, I made a mistake. It's not. I used the very first value. No. These are the values that we've got after the step 1. And those are going to be the value we have got after the step 2. So the value after step 2 are these one. So x equal to 0.459, y equal to 2.5199, 2.5199, z equal to this one, so 2.069, and w equal to this one, so 4.8999. There we go. So there we go. Those are the values that we have just found after those two full steps with the full cycles. Okay, so basically, so why did I get? Oh well, this one actually was should have really been 2. Forgive me. So it should really be in this one, which is the one of the first iteration. So 2.77. Oh wait. Okay, so those are all the values that we have just found with the very first iteration. Those are the values that we found with the second iteration. So basically, as I said, the Gauss-Seidel method has a clear advantage over the Jacobi method that we had just made, because in the Jacobi method that we have just made, we had a matrix in the R4, so the four-dimensional matrix, the four-dimensional space. We basically found x, y, z, and w in function of the other variables. We started with the iteration, but compared to the Gauss-Seidel method, when we found a very new approximation, like best guess and so on, for the variable, so in this case x and so on, we haven't used it. So we said, okay, this is gonna be our best guess, our best approximation for x, but we're still gonna use our initial best guess, so our initial value, in order to compute y, and in order to compute z, and in order to compute w. And then once we have done all those things, we found all those all the variables, we're going to go to the iteration 2, we're going to do all the step again, and in this case we're going to use all the variables that we had just found. So you can basically see that you're not gonna take advantage of the improved accuracy that you're gonna get by using the by finding the variables. So this is the Jacobi method. While in the Gauss-Seidel method, once you find x, for instance here, you're gonna replace the value the value of x with the value you had just found. So you're gonna take advantage of the improved accuracy. Therefore, the Gauss-Seidel method is gonna converge faster than the Jacobi method that we have just used here. So I would say that the Gauss-Seidel method has a clear advantage. There are still scenarios in which you can use the Jacobi method. Nobody stops you from doing that. But if you are in real life application, you have to choose whether you're going to use the Gauss-Seidel method or the Jacobi method. I will strongly tell you, don't bother with the Jacobi, go for Seidel, Gauss-Seidel. All right, so I hope it helps, and I'm gonna post one more video and upload one more video about the Jacobi method for solving system of linear equation, and after this I'm not gonna post any more video about the Jacobi method, I think, unless you ask me to, and in which case I might, but I'm not gonna do this anytime soon anyway. So I hope it helps. See you soon. Bye. Cheers.